So back to Preflow-Push. So we had analyzed in Preflow-Push algorithm the number of relabels. I guess it's spelled that way. Number of relabels is equal to n squared, bounded by n squared. In fact, we could be precise in terms of putting a constant there, and the book does, but I don't think that's necessary. Have I turned this on? Yeah. Thank you. And we also did the number of saturating pushes. That was big O of nm. So m is the number of edges, n is the number of nodes, and so we're making progress here, and both of these are pretty reasonable polynomials. So the algorithm looks like it's reasonably efficient. Of course, we have to have a data structure for identifying the nodes that have, or a node that has excess, and figuring out where to push and so on. But those are really quite small details. So it's clear that if the number of relabels, the number of saturating pushes, and the number of non-saturating pushes, if those are all nicely bounded, then the running time of the algorithm is going to be polynomial also. And so now what we're interested in is the number of non-saturating pushes. Okay, and so remember what a non-saturating push is. Here you have excess at V, so EFV is greater than 0, some excess there. And you have an edge in here which allows you to push on it. So that edge certainly has to be, it has to be in the residual graph. We don't know whether it's a forward or backwards, doesn't matter. I mean, at this moment of detail. And we also know that we have to have HV greater than HW, but we said last time that this condition, along with the condition of compatibility, meant that in fact HV is equal to HW plus 1. All right, so that's what we know about this edge. And when we push, if it's a non-saturating push, then all of the excess at V gets pushed out along this edge. So we know that the residual capacity, call it C prime E, that's the residual capacity, C prime E was greater than the excess. And that's why this is a non-saturating push. It doesn't saturate this edge. But after this push, after the push, then EF V is now equal to 0. There's no extra capacity. There's no extra there at that node V. That's what a non-saturating push means. Okay, so how do we bound the number of those? Well, first thing we do is find our notes. Okay. So this is a very pretty kind of argument that's going to bound the number of non-saturating pushes. It's something that's called a general kind of argument that's usually referred to as a potential function, a potential function argument. That just means it's a kind of indirect argument where there's some other thing that's going to be counted. Yeah?
Regarding the non-saturation push, what if the amount of push is less than the EFV? In this case, still non-saturation?
So you're asking if it happens that the residual capacity is less than EF. Well, then it would be a saturating push. Because let's say that we had an excess here of 10, but the residual capacity here was only 8. Then, according to the push rule, we're going to push out 8 here, because that's the minimum between the residual capacity and the excess. And that would saturate this edge, and then this edge would go away. So non-saturating pushes exactly means this condition. Okay, so let me erase that so it doesn't. All right, so potential function it just means we're going to be indirectly counting something, and this is what we're going to count. This function fh, theta of or phi, or some Greek letter. What is that? Phi, theta. It's what? Phi. Okay. I don't know. Anyway, that's the summation h of v. So it's just the summation of the heights of all the nodes that actually have some excess. Okay, so you're looking at the algorithm as it's running along, and at any given moment, there are certain nodes that have excess, and they have heights, and you can sum those up. And that's what this function is. I'll just call it function. The potential function. And where does it start? Okay, so this thing at the start of the algorithm, okay, because I should have defined, I guess, that the source is not considered to have excess. It has, infinite supply there, but that's not considered excess. So initially, it's just 0 because we haven't pushed out anything from the source, and we also know that it never goes. It's never negative, okay, because these heights only increase; they never decrease. All right, so now let's look at what happens to this function during the algorithm. So you're watching this function change as the algorithm does its work. And the algorithm, we know, does 3 kinds of things. It does a saturating push. It does a non-saturating push. Saturating pushes, non-saturating pushes, and relabels. Okay? So what happens to this function when we do a relabel? So this is relabel. Relabel. What happens to this during a relabel? It just increases by 1 because every relabel takes the node that's being relabeled and changes its h by +1. It doesn't affect whether that node has excess. Oh, and we only have done a relabel for nodes that do have excess. We're looking at a node that has some excess, trying to push it out, not able to, and then the h is increased by 1 for that node. So that's definitely part of the sum. That node is part of the sum when we relabel, and so this function increases by 1. Okay. Well, we already know that the number of relabels in the entire algorithm is bounded by n squared. Okay? So that says that, so the total, I don't know what the right word of this, upward contribution to this function by relabels is order n squared. Okay, so again, you think of this sort of as a movie. You're watching the algorithm go, and you're watching this thing change, and if it's increasing, or if there's a relabel, then you're seeing, okay, this increases by 1 at that moment, and we realize now that over the entire algorithm, the amount of increases due to relabels is bounded by n squared because there's only n squared relabels possible. Okay, what else can happen? Well, what happens with a non-saturating push? Okay, and this is what we're ultimately trying to understand is how many there are, but it comes out in this indirect way by looking at this potential function. So what does a non-saturating push do to this function?
It increases by the node that, the one that excess would reduce to 0.
Okay, that's half of the story. So what was suggested is that it decreases this by the height of the node that is doing the pushing, or the push out of. But there's also a possible positive contribution that's happening too. Okay, so let me just draw a picture. You're doing a non-saturating push from V to W. Again, because we're trying to push, V definitely is part of this sum. There has to be excess there. And because it's a non-saturating push, we know that after the push, the excess at V goes to 0. So now V is no longer part of that sum. So that would decrease, that acts to decrease this by H of V. But there's a possibility that something else gets increased. Yes, it's possible that W before the push did not have excess. It's possible that W but has excess after the push. Okay, so the change. Well, okay, so phi of FH decreases by H of V and may increase. I'm talking about locally. You know, you're watching this number, this function, and during a push you see it decline. Maybe just after the liquid leaves V, you know, this thing immediately changes, and then when it hits W, if W didn't have excess previously, then it increases. Anyway, it increases by H of W. But what do we know about H of V and H of W at that moment? Yeah, we said it over here that H of V is equal to H of W plus 1. Okay, H of V is bigger than H of W. Okay, but H of V is equal to H of W plus 1. So overall, this function decreases by at least 1 for each non-saturating push. Okay, so again, during the algorithm, you have various forces on this function. When there's a relabel, each relabel it lifts this function up by 1, and each non-saturating push decreases that function by at least 1. Okay? Well, what else do we have? We have saturating pushes. What happens to the function during a saturating push? Well, yeah. So I'll just draw this again. Here's a V, here's a W. This is a saturating push. Again, because it was a push at all, V is definitely in the sum. Okay, the sum over here is the summing of over the nodes that have excess. So V has excess. Being a non-saturating push, a saturating push, V remains with excess. We didn't push out everything. And so I guess there's a tiny degeneracy here. What happens if the excess amount is equal to the residual capacity? Do we consider that a saturating or non-saturating push? Well, yeah, if this has, it probably doesn't matter. But anyway, let's just, we're considering really here the case when there's some capacity, some excess left in V. Okay, so when V is left in the sum after the push, that H is whatever it was, it's still in the sum. Okay, W, if it previously had excess, then that was also in the sum, and therefore the saturating push had no effect. But it is possible, just as we saw in this case, that W did not have excess previously, but now does. Okay? All right, so this function can increase by, at most, h of w. Okay. That's during a saturating push. And how big can h of w ever be? Hmm? 2n minus 1, yeah. We did that last time, and in fact, that was part of the what led to here. Well, that's exactly, I mean, we established that, and then that immediately gave us that the number of relables is at most n squared. So we did this fact in detail last time. So this can increase by at most that much for a saturating push. And how many saturating pushes can you have? Well, we did that last time. The number of saturating pushes is at most nm. And so if each time is a saturating push, it can increase this function by at most 2n. And there can be at most nm saturating pushes. So altogether, saturating pushes can contribute n squared m additions to this function. Okay, everybody see that? So again, if we're watching the algorithm and we're watching this function, whenever you do a relabel, function goes up by 1. If you do a non-saturating push, then it decreases by at least 1. And when you do a saturating push, it increases by at most 2n minus 1. Okay? And then we also know, therefore, that the increases, the total amount that this thing is being increased due to a saturating push is bounded by that. We know that the total amount that it can be increased due to relabels is that. Okay? So, and it never goes negative. So these two act to increase. The non-saturating push acts to decrease. It never goes negative. So how many non-saturating pushes can there be? And each non-saturating push decreases by at least 1. That's important. It's at least.
Big O n squared m.
Yeah, it's this plus that. Okay? And since we were talking about big O, this is a bigger big O than that is. And so this implies the number of non-saturating pushes is big O of n squared m. Okay? So those are the three those are the three operations, really, central operations in the algorithm. Relabels, saturating pushes, non-saturating pushes. We've bounded them all nicely. Now we have to talk about one should talk about implementation. How does the algorithm find a node that has excess? Well, that's pretty trivial. I mean, it's just keeping what the total is in minus out every node, and some list finds a node. Then it has to look around the edges that are out of that node in the residual graph to decide, what it's whether it can do a push, whether it has to do a relabel. All the implementations issues, of course, are important to do the final analysis, but I'm just going to rely on your intuition to say that, in fact, they can all be done in this time bound. And at any rate, we were trying to prove termination and polynomial time termination of the algorithm. So it should be pretty simple to see, even if you don't do the fine analysis of the data structures, that each operation can be implemented in some polynomial time bound. So you multiply this by that, whatever that bound is, and you're still getting a polynomial. Okay, so m can be as big as n squared, and so if you want to just analyze this in terms of n, what we've established is that the algorithm runs in a time bounded by n to the fourth. Okay, so that's pretty good. And the question I was thinking of asking on the midterm, I decided not to, so I might as well ask it right now. Given this, have we now proven the maximum min-cut theorem completely? Because after Ford-Fulkerson, we had only really established it for integer capacities, or anyway, rational capacities. Well, anyway, if you think through the whole chain of logic of where the maximum min-cut theorem came from in our proof of it, all that was required is that the algorithm actually end up with a maximum flow, and then from the maximum flow, there was a minimum cut that could be found from that maximum flow, and then that was used to prove the max flow min-cut theorem. The only thing that was still left hanging from the Ford-Fulkerson was termination if the capacities were irrational, as we had proven termination for rational capacities. Well, this discussion doesn't say anything about the capacities being integer or real or whatever. Okay, non-negative, yes, but other than that, nothing. So we definitely have now proven termination of this algorithm, and therefore the max flow min-cut theorem for all networks with non-negative capacity. Okay. Now, the next thing that the book does is to show how to improve this n-fourth down to n cubed, and that's the next thing that historically happened. It is not actually that difficult. So, in fact, there are two ways of doing it, but the book only talks about one of them. And this is just a small implementation detail, but it then affects the analysis. And the implementation detail is just the following. So this is an improvement. If there's a choice for which node V to push from, so far in the algorithm, the only thing we required for from V or about V was that it had to have excess. The algorithm just picks any node that has excess and pushes it. I mean, there's another nice aspect to this algorithm because it's really decentralized. It's not like it's flowing, following some molecule of water through the network the way Ford-Fulkerson did. It can just look and find a node that has excess and do run the algorithm at that point, and so on, and make these kind of decentralized decisions. Which also gives some hint is the fact that you can parallelize this algorithm a little bit. But at any rate, there was no choice specified for what V is, except that it have excess. Okay, to push from. That's ungrammatical, but anyway. If there is a choice for which node V to push from, and this was the only condition we had so far. Now here's the new one. Choose the node V with maximum HV over the nodes that have excess EFV greater than 0. So just push from the highest one. Now, you could imagine maybe another idea is to push from the one that has the most excess, or some other rules like that. And there are other rules that people have examined. But this one is pretty easy to analyze. So this one just says, if I have a choice, always take the one that's highest. Another possible rule is maybe choose the one that's furthest from the terminal, or from T, or something like that. All right. Well, the advertisement is that we're going to get down to n cubed from n fourth. Well, already, if you look at the bounds we have, for the relabeling, that's bounded by n squared. Okay, the number of relabels is bounded by n squared. This is when we didn't specify which node to push from as long as it had excess. So that we don't have to do anything with that. We don't have to do anything with that for the same reason. M is at most n squared anyway. So it's the issue of the non-saturating pushes. Okay, so the non-saturating pushes before in our analysis we said that that's bounded by n squared m. And if we can bring this down to n cubed, then the number of operations in the algorithm, number of these operations is n cubed, and I've said before the data structure issue isn't that severe. Okay, so that's the change, and so we're trying to bound the number of non-saturating pushes. All right. Well, this one has a different kind of analysis. There's that. Okay, so give this a name. This is just called H, is the maximum. And so now, instead of watching this function, because we use this function to establish, well, actually, this was only used for the non-saturating pushes. So now we're going to watch H as the algorithm goes along. All right. So again, we're going to talk about what happens to H when we do saturating pushes and relabels and non-saturating pushes. So what happens to H when you do a relabel? It goes up by at most 1, or well, instantaneously. Okay, so at the moment when you do the relabel, H has some value, and then what happens to it when you do the relabel?
It goes up 1. I guess I was thinking of the max of H goes up. Right?
Yeah, H is the max of of all the little h's, and this, when you're using this rule, again, you're going to use, now we're using this modification. So maybe maybe the question wasn't clear, and that's why people said at most H, at most 1. So with this modification, when we're looking at a node to push from, it's the node that has the maximum little h. Okay, so if it's relabeled, if it can't push, it's going to get relabeled by +1, and therefore the max definitely increases by 1. That's what I was quibbling about, was the at least 1. It should be exactly 1. Okay, so a relabel causes H to increase exactly by 1. So the total upward contribution of relabels I guess to H anyway. It's again n squared. Okay, or another way of saying it is. But we already knew that the relabels are bounded by at most n squared of them anyway. Okay.
Explain that again. Why big H goes up by 1?
Why H goes up? Capital H goes up by exactly 1?
Yeah.
Well, because in this modification, when we're looking at a node V to try to push from, it's the node that has the maximum little h. Okay. And then if you can't push from it, you only relabel because you can't push. Well, anyway, you're relabeling that node by increasing it by +1. It's little h by +1. Since its little h was equal to capital H, that means capital H is going up by 1.
What if I choose to relabel another node till it has an equal little h, and then push from that node?
You can, yes, if there are ties from who has the max, you could be looking at, instead of V prime, but V and V prime are just pseudonyms, right? To protect the innocent. I mean, you're always looking at a node that has the maximum capital H, whether they're ties or not. And if you can't push from that node, you're going to relabel it.
Well,
and therefore the maximum goes up by 1.
Why would I necessarily relabel that node?
Because that's what the algorithm tells you to do.
That's the improvement on the algorithm.
The improvement is that I also only relabel, not just push.
No, that you always start with the highest excess. Before the algorithm, you could pick any old node that had excess and run the algorithm. Now you're always going to pick the one that's at the highest age.
Yeah. the relabel operation, remember, whenever it's looking at a node that trying to push excess out of it, and it can't, it relabels that node. And in the past, that it didn't matter which node that happened to be as long as it had excess. Now with the modification, it's going to be a node with maximum little h, and therefore it has maximum capital H. And then when you relabel, it has increased by 1. Okay. All right, so H cannot go down, but all right, so what happens? H can only increase. Yeah, and how can capital H ever change? Okay, oh, sorry. What provides the upward force on capital H? Just the relabels. Okay, and so the upward force on relabels is bounded by n squared. Okay. Now how do we know that, by the way? What if we did a push from V to W? Whether this is saturating or non-saturating doesn't matter. You do a push from V to W, and W previously didn't have excess, but now it has excess. The claim is that capital H doesn't increase in this case.
The height is less than.
Yes, because we know anyway, whether or not this is the max, it didn't even matter, but we always had that relation if we're pushing. So, well, and now capital H is equal to that, to this one. So if W now has excess, the max is not going to change. H is still the max. Okay.
If it is non-saturated, what if it is saturated?
Oh, okay. Sorry. Yeah, I was analyzing the upward push, the upward force on capital H. Okay. Yeah, it's possible that if this is a non-saturating push, therefore V, its excess goes to 0, it's possible for H to go down. Okay, but we're just analyzing whether a push can make capital H go up, and it can't, because a push always goes from a node V to a W, which has this relationship, and therefore H of W is strictly less than capital H. Okay, so a push can't make capital H go up. The only things that can make capital H go up are relabels. Okay, it is possible that a push can make capital H go down. All right, and that's what we're seeing in here. All right, and in fact, it's well, let's do the analysis here. A saturating push does not change capital H, because in a saturating push, this had excess before the push, and its little h value is capital H. But after the push, it still has excess because it's a saturating push. This was the limiting factor, was the capacity here. And so capital H doesn't change. All right, a non-saturating push can decrease capital H because, well, in fact, no, it can. That's the only word, can, not will. When you push from V, it's a non-saturating push along the edge. Therefore, V's excess goes to 0. So it's out of the game of being the max. Maybe some other node was tied. Maybe some other node had an H value that was tied with it, in which case capital H will not go down. But it is possible that capital H will go down by 1. All right, because in fact we know that H of V is equal to H of W plus 1. So it can happen that the capital H value goes down by 1. All right, so we've got relabels. They can totally, at most, increase a capital H by an n squared. We have saturating pushes. that don't change capital H, all right? And we have non-saturating pushes. Ooh, that's not good. If we had each non-saturating push definitely decreased H by 1, we have each non-saturating push definitely decreases H by 1, and the increases can be at most n squared of them. Therefore, we would bound the non-saturating pushes by n squared, which is what we're trying to get at. But I'm a little confused here about this. Yeah.
I think that they always decrease H by 1 because I don't think there can be a tie between two nodes V and W. I don't think there can be a tie for H value because if there was a tie for H value, then one of them must have been lower before it was relabeled. So like, if H of V is equal to H of W, then either V or W must have been relabeled. So let's say H of W was less than V the previous iteration, then you wouldn't have chosen H of W, you would have chosen H of V. So and if you didn't choose H of W, you couldn't relabel it to make it higher.
So you're essentially claiming that the max has to be unique. There can never be a tie for max. If there's no tie for max, then the non-saturating push will definitely decrease by 1, and that's good. Then everything is fine. All right. So, but if there was ties, let's say there's somebody else out here, a V prime, where H of V prime is equal to H of V, then I'm stuck here because the non-saturating push might have decreased H.
I don't think we're stuck. I don't think we're stuck. If it's an n-way tie,
yeah,
then we can do a non-saturating push with a big H value of whatever the big H is at most n times, because they're at most
that's
n.
true.
And so we can, and after n iterations, we know we've decreased big H by 1.
Yeah.
Since there are n squared of them, we do a non-saturating push n cubed times, and we should be okay.
Oh, yes, I'm sorry. Yeah, okay. We're not shooting for an overall bound of non-saturating pushes of n squared. That's, yeah, if there was unique, we would have a wonderful result of an overall bound of the number of non-saturating pushes of n squared. What we're shooting for is a bound of the number of non-saturating pushes of n cubed. Okay, so we get to play around a little bit. All right, so each non-saturating push can decrease H, but we don't know whether it does or not. It wouldn't if there's some ties. Okay. But ties, what do ties mean? Ties mean that there are all these other nodes out here that have the same H value, which is capital H. Okay? So, all right, we looked at this node that has capital H, its little h value is capital H, and we do a non-saturating push, and maybe, the capital H doesn't go down because there are these ties. All right? But then we have to go and look at each one of these and try to push from them. Now, there can only be n of those, because there are only n nodes in there at all. None of them are going to push back to here, okay, because this is capital H. I mean, you can't push from one of these nodes to one of the nodes that you'd already pushed from that had been capital H, because the rule for pushing says that this little h value has got to be strictly bigger than this little h value, but in fact they're tied. All right. So the point is that for any fixed value of capital H, when capital H, if you're looking at some point in the algorithm, when there's a whole series of non-saturating pushes that are happening, or pushes that are happening where capital H doesn't change, there can be at most n of those. Okay, so let me say that again. You could come to some point in the algorithm where capital H, you do some successive pushes and capital H isn't changing. You're not relabeling it all. You're just doing these pushes. Some are non-saturating, maybe some are saturating. But how long of an interval can that be before you do some non-saturating push? Well, you can't. First of all, at that start of that interval, there's at most n nodes that have capital H as their height, because there are only n nodes at all. And when you do a non-saturating push from one, this edge, that edge stays there. Anyway, it goes to 0. But the point is, its H value, its height, doesn't change. All right. And then you may have some other nodes that have height at capital H, so you do some pushes from them. But you can only do n of those before you have to do something else. Why? Because you've run out of excess at each one of these nodes. Okay? You've gotten rid of all the excess there, which, and if you get rid of all the excess at all the nodes, then the algorithm terminates. Okay? Why do we know it can't get any more excess? It can't get any excess when we're doing pushes from these nodes, because they can't push from here, for example, to here, because the requirement of doing such a push is that this height is strictly bigger than this height, but in fact they're tied. All right. So we can have at most h of these non-saturating pushes in a row. Okay?
But don't they have somebody to push to, though? I mean,
well, yeah,
how can there be n? If there's only n nodes total, how can there be
well, if there really were n, so this is an analysis. It says at most n. If there really were n, then there'd be nobody to push to, and we'd run into, we'd have to be finished at that moment. Okay, but it's possible that you're pushing here to something whose height is h minus 1.
Oh, you're talking about n at layer h, okay. Not
Yeah, right. There's at most n at layer h.
okay.
Okay, so you can do, right, you can do at most n of these things where you're doing these non-saturating pushes and where we don't decrease h. Yeah.
I actually think there can't really be a tie, though.
Sorry.
I actually think there can't really be a tie, though, at where h of v is equal to h of v prime.
No, I think there can be ties.
Well, if there was a tie, then that means that at some point one of them was incremented to the other one. Or well, okay, no, maybe I'm wrong. I could talk after.
I think it can happen. There'd be ties. Otherwise, we would have proven an n squared bound instead of an n cubed bound on the number of non-saturating pushes. Okay, so the conclusion here is that the number of non-saturating pushes we can do in a row is at most n, and without actually decreasing the height. Okay, so for every n non-saturating pushes that we do, we're ending up decreasing the height by 1, and we know that we can at most increase the height by n squared, and so we've got these n non-saturating pushes for each increase of 1, and that gives us a bound of n cubed. All right, so the total number of non-saturating pushes is bounded by n cubed. And that's where we were going. That's what I advertised was going to be the improvement. Instead of n fourth, now we have n cubed, although there's still the data structures issues of how you implement this without that exceeding your time bound. Okay. Well, I'm sorry this got a little bit disjointed here. I wanted to actually